Hello, folks. So this is Frank. We're going to do some more differential data flow programming today. What I wanted to do was to resolve something that I just got back from Sigmod, and I said two things at Sigmod at two different times that were in conflict with each other, and I wanted to resolve that. So one of them was in the presentation for this paper here. Unboundedness and efficiency of truss maintenance in evolving graphs. I'll try to explain what that is, but the paper is about a specialized algorithm for a particular problem, and they show that they get some good numbers at the end that improves on the state of the art. And I had asked, is your specialization substantially better than what you get using something just a bit more general, like not even trying too hard, just using, let's say, differential data flow, which I was sincerely interested in. My sense is that they were not as interested in that. They're interested in looking really hard at specific problems. So that question was left unanswered. But later on, I myself gave a talk and said in that talk that as part of doing science, we should make sure to essentially to aggressively test each other's hypotheses and claims. So what I thought I should do is actually try this out. These folks don't have experience with differential data flow, so there's no particular reason to expect that that's the sort of thing they would run out and test. But I thought I would learn a little bit about this and go and try to implement it. A little bit of a caveat here. I actually already know what the problem is. I saw the talk, first of all. I know what the problem is, and it's not a bad fit with differential data flow. So we aren't just going to hit our heads directly into a wall. Though I did, and I'll try to reveal this as we go along, I did spend 10 minutes doing just a brain-dead implementation in differential data flow. And I thought it was very clever, and it's terrible. But there's lots of really cool potential optimizations, different ways to structure the computation, and I'm pretty sure that we're going to learn something one way or the other. We may not actually do as well as this particular paper does. We might. My sort of stretch goal is to do as well as the prior work did. So they improve on stuff that came before, in some cases by up to 3 orders of magnitude. So, like, if we can land within 3 orders of magnitude of these folks, I'm pretty happy. It'd be better if we could, But let's see how far we get, basically. And by the time we get there, let's see if you agree or not that, this is still a general purpose computation platform, or if I ripped everything open and basically lied all over the place. So, I'm just going to create a new project. Where are we here? Home directory. So CD projects, a work in progress directory that I'm using. I have some other random bits of just dirty files, but let's do cargo new graphs. We're gonna have a few different graph algorithms that we implement, I think, because I think we want to build up to this particular problem. It's not the first thing you would try to implement. So if we wander into graphs and we nano up our cargo.tuml, I'm going to add a few dependencies in here. We're going to start just with timely, which I'm going to use GitHub releases for this, because we're going to eventually need to switch over to something that isn't actually publicly released. It's in the repos, but it's not on crates yet. So we'll do git equals, how does this work? Crap. ps://github.com reading out loud is great. And we'll do this again for differential data flow. Great. And like I said, we will need another crate in a little bit, but let's just get this started first. So let's cargo check what we have here. It's going to go fetch these things for us, and it's going to do some initial building of just lots of crud. We don't even have a program yet, and it's going to take... anyhow. So let's see. Let's crack open projects, work in progress, graphs. And we'll shut down this one. So over here we have a main. It doesn't really do anything yet, but we're going to add some stuff to it. So let's see here. What I've done already, actually, is if we look at the paper, they talk through a few things, but by the time we get to their evaluation section, they have pointed us at a web page where we can get some of their graph data. I went over there, this is the Koblenz Network collection, and I grabbed some of the data. In particular, I grabbed the smallest and largest temporal graph that they have, which is the, you can see here, the Facebook graph and the YouTube graph. Neither of these are very big, but that's fine. We can still screw things up really easily on small graphs. So I have these two in my hot little hands, and I thought we'd start out just by writing the little bit of a shell that will load these up for us and do something. Well, maybe we'll start with just like computing triangles or something like that. So let's write that out. So we're going to do sort of standard timely execute from args where, if you recall, a lot of our timely data flow programs look like step one, initiate a timely data flow computation. And the timely data flow computation is essentially we shell out to this timely execute method and say we will now program each of the worker threads. So we're going to write a little closure here that says what should each worker thread go and do. And for the moment, we're going to do something simple. Let's just try to find the file, some file from the input, and read it. And I think in particular we're going to need to sort it by the timestamps that are in it so that we can put it in order to play it at the system. So let's just do like let file name stood args so let's must supply a file name. Great, now we've got a file name. I've got a few other things in mind, so let's also grab a batch size from our arguments. So this is actually here's a better way to do this, which is a bit more robust. Let args mute args stood. So rather than just guessing all these random locations, which are going to maybe change if we had some new argument, we'll just grab the arguments. It's an iterator, so we'll grab the arguments. We'll remove the first argument. That's going to be the binary name from the program. And now we can just say repeatedly args dot next. And batch size should also be args dot next, except we're going to go and try to parse it rather than just take it as a string. We'll supply a batch size, try to parse it as a usize, and then complain if we can't parse it properly. And we're also going to grab something which I'm going to call inspect. This is basically, when we run these sorts of programs, it's occasionally helpful to have, because things don't go right, occasionally helpful to have a little flag which says, should we look at the output or not? That way we don't have to recompile it each time we change our mind about whether we want to see some output or just see some timings, maybe. Must indicate inspectiness. And this is just going to be a bool. It's either true or false. And inspectiness. Just autocomplete it. Must be a boolean. I guess probably George Boole was a person with a proper name, and so we should respect that. He's from Cork, Ireland, apparently. That's something that the people in Cork are quite proud of. So now that we've pulled some arguments down here, let's actually crack open the file reading part of this. So we are going to use stood IO because there's some important traits in there. Buff read and buff reader. Reader is a type, I guess, not a trait. Std fs file. And what are we going to need? We're going to want to hold the edges somewhere, so let's do let mute edges get spec new. We'll grab a file, let file, it's buff reader new file open file name. This is a result because we might not have found the file, so we want to say something like expect could not open file, which is exciting. And now this file thing that I have here is a what's a buff reader, something that we can read lines of text out of. So let's do that actually. Mute lines gets file dot lines. This is now an iterator over lines, so we can start reading out of this thing. And I happen to know, because I looked at this before, that if we look at the data sets, and this is the small one. We got two lines that start with percentages, and all that I'm going to do is this is terrible. All I'm going to do is just call lines.next twice, just to discard these. We could have a more complicated filter, check to see if the line starts with a percent thing or something like that, but we're not going to do that here. All right, we're going to want to walk through these, and I'm going to write this as if we're doing multi-worker stuff from the get-go. So this is just good hygiene in timely data flow. Otherwise, this is a classic bug you find yourself making over and over again. We're going to count out the lines so that we can distribute them across workers. So we read a line, so we count read line. Lines is this iterator. We can enumerate it, right? That's the thing that turns it from an iterator over lines into an iterator of pairs of integers and lines. And we can now do if count mod, what do we got, worker dot peers equals worker dot index. So this will distribute the responsibility for these lines across all of the workers. And that's good because it's a little annoying to parse all this data in because parsing is slow. More on that later. All right, so these lines are not actually text yet. They're actually just the results because there might have been some error parsing thing. So we need to do the following, where we say, okay, only in the case that this was a successful read of a line, we want to take our line of text and split it apart based on, let's see, based on white space, I'm pretty sure. Yeah, so there's just some white space in between these things. And I don't know exactly what's going on here, but this is, the first two things are parts of the edge. The third thing, no clue what that is. And then this last thing is a timestamp. So we're going to want to grab those three things. So Rust has a split white space method, which just splits in all sorts of white space, things like tabs and spaces, and maybe carriage returns too. It's pretty cool, right? So we're gonna pull out this, and it returns an iterator over string slices. So it doesn't even create strings for us, which is cool. It means that if we're gonna go and just parse what we see there, we don't even need to worry about having done the allocation to get one of the pieces of text back. We'll just get to see it as a little bit of a pointer into the larger string that is line itself. So we'll do field.next. I'm just going to be lazy here, unwrap. We'll see if it explodes. But basically, we're hoping that each of these lines are properly formatted. They were when last I tried this, so good. We're going to parse, we're going to unwrap. And let's, we don't want to type here. Let's just make, we want type node u32. We'll do the same thing now for our destinations. We don't have to type anything new because the iterator has advanced by 1, so we're just going to grab the next field. We want to skip the third field, fields.next, just ignore it. And then we're going to get our timestamp out. And it is not necessarily a 32-bit integer. Maybe, it might be actually, but let's make it be a U size just because we don't really know. And then in our edges collection, let's push these triples in, and what I want to do is do time first, time source test. This is going to let us sort edges in just a moment by timestamp, and that's going to be useful because when we run our computation, it might be nice to sort of do it in timestamp order. That's what the nice folks from the paper back here from I think Chinese University of Hong Kong, sorry, have done. So we're going to do that also, and I think it's time to do that. Edges.sort. So now we have some edges in order across each of our workers. Let's see if this actually builds. No. Why? Oh, because it's confused about what we're returning. Great. So let's actually run it on some stuff. Just this. Let's run it the release mode. Projects. We need to change the code just a little bit before we run it because I want to print like a length or something like that. Data sets out. Facebook. What do we have? We had batch size, not used yet, and inspect, not used yet. But let's do just here println. Actually, I know what we can do. Edges sorted. We're going to do a fairly standard thing up here, which is to grab the timer, worker.timer. This is just something sort of handy. Each of the timely data workers has an internal timer that they're maintaining. They use it for things like logging and stuff like that. But it's also helpful for us to use just to see how long did various things take. Timer.last. Great. And maybe actually we could do one before and say edges loaded. See how long it takes to sort things versus load them in. My guess is loading them in will take longer than sorting them, but that's just a guess and also pretty irrelevant. Yep. This is compiling a whole bunch of timely stuff here for no particularly good reason. I mean, we've not written a complicated program. It is not going to do anything particularly interesting or complicated. It's not going to use any timely data flow infrastructure. But Rust does not know that, and it eagerly compiles a lot of code that it does not need to use. But ideally, it won't do this again the next time, or it'll only do work proportional to the changes in our actual program, not in the underlying dependencies that we're currently sorting through. This is, I guess, Serde that we're waiting for mostly, which again, we're not serializing any data. All right, almost there. Super exciting. Will it print the correct length or won't it? Will it crash? Okay, we're now actually compiling our program. All right, and we loaded some data and sorted some data, and oh, I was totally right. It took longer to load than it took to sort. Let's double check that we can do multiple workers. Yes. We didn't report how many edges we loaded, so it's a little hard to know if we actually distributed the work properly. We don't appear to have gone any faster by using multiple workers. Shall we? Let's just double check. We're not going to have to recompile the whole thing, fortunately. Edges.blend. So hopefully this will just take 10 seconds or something. 5 seconds, good. All right, so we can see that there's slightly different numbers of edges there, which makes sense. And it looks like they probably add up correctly. So great, good news for us. We could use this. Let's try a slightly larger input file just to see if we can actually make the numbers of workers matter or not. All right, that was one worker, and you can see this; it's bigger there. A little faster. Anyhow, yeah, cool. All right, so we've got the graph data loaded up. It's loaded up. It's sorted. Let's think of something to do with it. So, yeah, so let's build a data flow, and then maybe let's put some data into the data flow. What's a good idea? Let's start just by, okay, so the code is going to look like, worker.dataflow. Scope. And let's start with something kind of simple. Maybe let's just start with triangles. So compute triangles from edges. Great. Let's see here. So the first thing we're gonna need to do is create a new input. We have our data lives out to these edges at the moment. We could just, if we wanted to, we could totally just check this out, right? We could totally just do edges.toStream, which take anything that can be iterated and turns it into a timely data flow stream. We don't want to do that though. We actually want to have a computation that is going to play these edges out slowly so that we can measure the time between, the elapsed system time between each of the distinct times that we use in there. So let's create a new new input thingy. So the way this works typically is we're gonna there's a new collection method on scopes if we import the correct trait. Use differential data flow input. Let's see. And that gives us back a, I want to say a handle and a collection. And the handle is the sort of thing that we're going to hand back from our data flow method invocation here so that we can use it in the outer scope. And the collection is what we're going to use internally. So let's just do something incredibly simple at the moment. Let's just do out degree distribution. So we're going to take our collection, which will probably be pairs source, dest. Let's grab just the first field, source dest source. Let's count what we've got here. So this is going to say for each source, how many times did it show up? That's tells us the out degree of source. So we'll, having counted these, have another source comma count, and we're going to do something just to get a feel for things. We're just going to keep the count. We're going to say no one's interested in the well, not no one, but we're going to ignore the source for the moment. Let's take the count, consolidate that up. So lots of different nodes might have the same count, the same out degree, and we're not interested in seeing one record for every single node that has an out degree of 5. What we'd like to see is all of those consolidated up, so the number 5 and how many nodes, or what the changes were to the set of nodes that had a count of 5. And let's inspect this. So we're going to do our timer.elapsed here, and we'll do x also. I think we're going to need to move there. And to be grown-ups, let's do a probe with here. This is the sort of thing, so we're going to want to do let probe equals timely data flow probe handle. This is the sort of thing that lets us know that a bit of the computation has actually completed. The data flow itself doesn't normally complete. Only at the very end of the computation will it. But the probe handle lets us see the partial progress of the computation. As we start pushing timestamps into the data flow, we get to see how many timestamps have been retired at this point. So what times will we never see again, basically. And let's see if this builds. Probably not. No method count. All right. this is a standard song and dance we have to do, where we have to use each of the extension traits to warn Rust that this is an exciting method that it should be able to find once we've given it a hint as to which trait it lives in. All right, now, okay, this is a standard problem. We haven't told timely data flow yet on what basis do we want time to advance. And we happen to know what that is. It's going to be U sizes up here. But since we haven't actually put any data into the computation yet, Rust can't connect the dots and say, like, oh yeah, okay, I see what you're using. So let's do it. Let mute handle equals, and down here we're going to return the handle that we got from our new collection. Having returned the handle, we can now introduce things. So we can, for example, we can write the following little bit of code, which is actually something that's going to be pretty general, and we're going to use it over and over again, which is the following. Using my notes to make sure that I don't screw this up, because it's easy to screw up. So we're going to iterate through all of these nice little these edges that we have. We're going to enumerate them, so we're going to count as well. We have them through called our time, source, and dest. And we've got them in edges. We're going to turn it into an iterator. We're going to enumerate it. Now, we've only loaded up a partial fragment of the edges at each worker, so we don't want to do that trick again where we test to see is the count mod the peer is equal to the index. Now we're just going to insert everything that's in here. We are going to take a break every now and again. So we will do input.insert of source dest. And we'll put a line in here. Actually, let's do this first. Advance to time. So before we put the thing in, we want to make sure that the time is correctly positioned, so that when we call insert, we actually insert it at that time. And if the count has reached a point where we think maybe it's time to go and do some computation, so we could, having inserted that one record, run the data flow and see like, hey, are you done yet? Which will be the case if batch size was equal to 1. We'll do exactly that. But we're just going to write slightly more general stuff for the moment. All right, input.flush. So input flushing is an important thing to do. When we call advance to time up above, we're not actually committed to anything timely data flow wise. We happen to know that we won't ever walk the time backwards, but we haven't told timely data flow that yet. So timely data flow, until we call flush, isn't actually in a position to reason about the various times that we've claimed to have advanced through. But having done that now, timely data flow can start to do computation and realize, oh, you may never go back to anything before time, and therefore I can make promises to the probe, for example, that, input. I'm just so used to input being the thing that I call it. So you can write this little very common idiomatic differential, or timely data flow even, which is that as long as our probe is something less than what our input is currently positioned at, that means that there's still work in the data flow that does not result from our ability to add new things. So we've added some stuff, maybe we've advanced our input, and there's still something not yet resolved. We should keep stepping. So worker.step will schedule work, and this keeps scheduling the work until the data flow is caught up to our input. And maybe this is a good time to, if we're for worker 0, let's println round complete. All right. I'm going to make these also be guarded by if worker index stuff. It's not exactly right because they might take different amounts of time to sort things, but just to avoid spamming too much. Great. So this now responds to our batch size. We've set that to be something. We will do different amounts of work based on that. Actually, let's make it respond to our our inspect thing as well. Inspect. One way to do that is to say, well, we only really care to look at these things. This is a fine place to do it. We only really care to look at this data if inspect is true. Right? So if inspect is true, we'll pass all the data, and if inspect is false, we'll drop all the data on the floor. We won't see anything. We will still have done the work up above. And perhaps we should. The consolidate I was thinking was only there for the benefits of inspecting things, but let's do that work as well. Cool. Now let's check and see. It's getting closer to build. It builds. Amazing. Well, looks like it might build. Amazing. We've got a few moments that we probably should go and acknowledge where we have not actually used our data. That's fine. We didn't mean to use it, but it's helpful, sort of idiomatic Rust, to go and put some underscores in front of those variable names to reassure other readers of the code that we're actually doing what we intended. This is now a bit more complicated because we actually have some data flow in there. That's exciting. All right. Lots of stuff. Basically, oh, okay, well, I thought it was going to take a while longer than that. Great, and we see things like, someone changed their out degree from 218 to 219. That's the very last thing that went on in our computation. Neat. And you can sort of see also timestamps are a little out of order. This has to do with the fact that we're putting in a batch of 1,000 updates at a time, and there's no particular obligation within these batches to have them print to the screen. Or like they'll be executed as if performed in sequential order, but when they hit the inspect operator, who knows, right? The inspect operator doesn't work that hard. There's a thing that we didn't report, which I'd like to fix actually. So we ran through all these things. We may still have put in some data and not gotten around to the next flush yet. So I wanted to do that. It's a bit different at the end. You do input.close. I mean, we could try to figure out what that last time was and flush and I suppose we could just do that. In closing the input is leave that there as a comment, is a thing that is worth thinking about doing. Let's close it, because we, although we're calling flush, we haven't necessarily advanced past the last time. And we don't really know how to advance past the last time without having access to the last time. So let's just do input.close. And now since the input is closed, there isn't really a time anymore. And we write something that's a little different. It's a little gross looking, actually, for which I apologize. So worker.step actually returns a bool. And that bool says approximately, like, are we as a worker done yet? Are there still data flows with work still in them? And if there are, we just want to keep calling worker.step, which this weird bit of code will keep doing. And it's not just a round that's complete anymore. Computation is complete. Whoops. Not only is the argument not used, the argument does not exist. I'm just going to throw in a few more things here for our next recompile. So this timely returns a result type that tells us about the state of all the threads, the worker threads. If that screws up, that meant that it had a hard time starting the computation. Great. Put some underscores in here just to make things look pretty. And hopefully the very last thing we see is a computation complete with a time. As you can see, this is starting to take an obscenely long amount of time to compile. That sucks. Great. So, hooray! And had we, this thing is turning into a jet engine. No, that's fine. Okay. Had we turned inspect to false, we would not be seeing all of this nonsense in here. We would just be seeing the various round completes that maybe we can, if we sniff around in here, we can see some of, maybe not. Fascinating. What's going on here? So we're apparently, this is a little surprising actually. Let's see if we've screwed something up here. We're supposedly putting in a bunch of data and then happily advancing to the various next rounds, and absolutely nothing is coming out in the output, which surprises me. Great. Oh, I know what's going on. Okay, which I was going to say which surprises me greatly, but I've now remembered what's going on. I think there's about 800,000 edges in here, and a lot of them are at time 0. So we've sorted all of them. A lot of them happen at time 0, which is to say, initially, if they're initially present. And it's not until we move our timestamp past 0 that we actually start computation, right? Like, if we keep putting zeros in, we keep saying, great, we got more zeros to do, then even when a batch boundary happens, we're going to say, okay, well, is our probe anything less than 0? And of course, it's not anything less than 0. So we'll just skip all of that, because in essence, there's no work to catch up on. Although there's data in the system, we can't finish any of it yet because we've still got more work to do at time 0. So this all happens super duper fast, and then we spit out a fairly obscene amount of data and start moving through rounds at this point. A bit more, see if we can find the next one. I guess we're going to watch this number scroll up until it, there we go. I didn't pay attention to how long that was. 398 here versus 385, so what, 13 milliseconds. Probably a lot of that was printing crap to the screen. You can sort of see on the side here that screen printing crap, there's quite a lot of it. Anyhow, great, so we've got our computation, we've got our test rig set up. We can do a few other things in principle. One thing we might want to think about doing is the following. Yeah, let's do this just to, it'll also tidy up our output a little bit. We'll be able to toggle back and forth between the two of them. But input.advance to count over batch size. Let's get this running in the meantime. Building. So what this is going to do is walk through in rounds 0, 1, 2, 3 based on our batch size and keep ticking in bits of data. This is going to remove lots of distinctions between different times. Actually, it's going to introduce, I suppose, now that I think about it, some artificial distinctions between all those people at time 0. But this is going to take, as the computation is actually running, it's going to take us down from every edge being at a distinct, these are millisecond maybe, to batches of them about 10,000. So we might actually see between the rounds relatively fewer distinct counts and distinct count changes, which is plausibly appealing. Yeah, so for example, this is sort of the full set of changes that happen between whatever the almost last round was and the final round. Took less time too, probably because of all the less printing. And this is potentially helpful because computationally, it lines up a bit more with what we're going to be asked to do in our project a bit later on. And also it doesn't show us all this massive detail of how every little widget changed at every moment of every edge addition, which is really cool to look at. And it's cool that we can compute it. We'll try it both ways. But it's just a bit gross to look at. Hey, why not? Let's just actually make a new parameter. Let round times, I guess, I don't know, equal args next must indicate round e-ness. Great. It's going to be a bool again. And round e this must be a Boolean. Great. So now what we can do is just if not round times and if round times, sweet. So that does the thing now. And we have to start writing things like true. There. All right, that's just going to be building and running in the background. So what we'd like to do next, I think, this is sort of mentally is a good point to take a breath. You know, we're ready to think about what sorts of graph computations we might like to do. And these people, the Chinese University of New York, Hong Kong, New York, what the Chinese University of Hong Kong people have done is this thing called truss maintenance, which sort of means that I should probably tell you what trusses are in graphs. And I'm wondering if I should tell you what they are first, or if we should build up to them. They involve triangles. Let me try to explain, and then compute. You know, we'll write code that builds up to this. So what a truss is. There's maybe a few ways to describe it, but one way to think about them is that an edge in a graph is called a k-truss if it participates in k-triangles. So we've got an edge from A to B. If there are k other nodes C, so that A, B, C forms a triangle, then we get excited about edge AB and we say that it's a k-truss. Now that's cool. That's a thing. One way that we can compute these, and we'll start with that probably, is to compute all the triangles in a graph, and then for every triangle, give 1 point to each of its participating edges, and then have the edges add up all their points, and that gives a number, which is the number of triangles in which they participate. So that'll be cool. We'll start with that probably. Now the actual problem here is not figure out how many triangles each edge participates in. That's pretty easy. Well, it's going to be computing triangles. The harder thing is something, I don't know if it has a name or if I've just screwed up the names, but the sort of the k-truss decomposition of a graph is to say, take your graph, figure out the value of k for each of its edges. And now, rather than that being the output for each of the edges, what we're going to actually try to figure out is for each edge a value k such that it participates in at least k triangles with other edges whose values are themselves at least k. This is a bit of a mouthful, right? But an edge is in the k-truss of a graph if there's a set of edges. The k-truss of a graph is the set of edges such that when we look at that set of edges, every single edge lives or has participates in at least k triangles in that graph. So if you had a lot of triangles you participated in with crappy little degree 2 nodes that didn't themselves actually participate in lots of triangles, yeah, that sucks. You're not gonna survive to be part of the actual k-truss of a graph, because all of the support that you got in terms of your triangles that contributed to your score are going to go away because the other edges in those triangles are not also part of this same truss. So, it's a bit of a mouthful, but it turns out there's a not so complicated algorithm to determine this. There's also some complicated ones, but there's a not so complicated one that essentially repeatedly says, let me guess at a level, like a value of k for each of these edges. Maybe we'll start with how many triangles in the whole graph do you participate in, and then figure out for each edge how many triangles it participates in at the moment. Give it a number based on that value of k, and go around the loop again. But now, when we form these triangles, keep track of the smallest value of k involved in each of the triangles. So this is the value of k that we need to be at, this value or lower, for this triangle to actually exist. Right, So if we had 3 edges, and they themselves had, let's say, 3, 5, and 7 triangles incident on them, then that triangle doesn't actually exist unless we are asking about the 3rd level or below. Right? So if we're asking for people who have at least 4 triangles that they're participating in, one of those edges goes away, that triangle doesn't exist anymore. All right, maybe this will make more sense as we start trying to code it up. Before we try to code it up, let's do something simpler. Let's do triangles. So this is our computation at the moment. Let's just start writing a new method down here, actually, which we're going to call triangles. Fun triangles. It's going to take a parameter g. The g is this scope parameter. So we're making this be generic with respect to any old data flow scope we might try to write this in. Our input is going to be a collection in G of edges, which are pairs of node. And we're going to try to produce what as output. So I'm going to leap ahead here and say that we're going to try to produce pairs of edges. This is so like type of edge equals node. Pairs of edges and a count, which I'm going to use the word node for. A count, which is going to be the number of triangles in which they participate. So I just don't actually want to return all the triangles here because there's a lot of triangles, and what we're actually going to want eventually anyhow is this count for each edge. How many triangles did it participate in? Great. We are going to assume that the edges that we find, x comma y, or sorry, source comma dest, are undirected, and we're going to assume that by saying that we assume that they satisfy a source less than dest. So we're going to take the edges, for fuck's sake. This is like no joke. Have do not disturb turned on, and the idiotic Apple Mail program still is like, oh hey, let me check your anyhow. Go. So actually, I'm just gonna quit that shit now because it's super frustrating how stupid it is. Right. So so we have these edges. They're ordered in a particular way. This is going to be important to make sure that we only, we find each triangle once instead of maybe 6 times or maybe 4 times or something stupid like that. So how do we find triangles? So we've got some edges. Let's do edges dot join. And I'll tidy this up as we go along. So edges. This is oops. So we're gonna join AB and AC. So it's exactly the same relation. Edges we're joining twice. We're just looking for 2 different things. We're looking for candidates for B in a triangle ABC and candidates for C by finding edges that emanate from a common A. And these are great. So let's map A comma B comma C to A comma B comma C. This is a little wrong right now because we want to filter these A comma B comma C because we only want to retain those for which B is less than C. But now we have a triangle A, B, and C, and we might like to now, since we have to produce these counts, for each of these triangles, so we'll do a flat map A comma B comma C. And we're going to return this is gross and horrible, but I'm not aware of a better version at the moment. We can try to fix this up as one of our many things. We're going to put out an AB edge. So we're saying for each triangle ABC now, what are the interesting edges in it? Because we're trying to award points to different edges. And these are the 3 properly directed from small to large edges. And then we return it. Yeah, pretty cool. Let's see if this builds. see if it builds once we put collection in scope. No, oh right, because we need. So I should show you these error messages, but sorry, we have some type constraints on G, so G needs to be a scope, and also G's timestamp needs to itself be a differential dataflow lattice. These are important bits of math that ensure that we, important bits of math that ensure that we're actually able to form the types and perform various bits of operations. Mismatched types. Oh, right, yeah, okay, sorry. So this returns, I wonder if we should, so what this returns, sorry, is collections of edges where the count, the multiplicity, is actually the thing we're returning. Let's do that, actually. This means we'll have to do our own count. We could have done a count, basically, after that to make this a little bit better. Type alias never used edge, really? Never use edge? Because I see it right there. 96, type alias never used. So that's probably a bug. Oh, no, I'm sorry, that's not a bug. We don't call triangles. So let's call triangles instead. Rather than do all of this stuff in here, we will, actually we're just going to skip one step really. So rather than just picking up the source, we're instead going to call triangles on collection, I think. And then we're going to count it. And this is actually source test. But we're going to count what comes out of here. Remember, what comes out of here are a bunch of edges with multiplicities. So we'll count them. That'll tell us for each edge how many triangles does it participate in. And to get some interesting statistics, we will say, don't care about the triangle, don't care about the edge, just care about the number of triangles. And then we'll be looking at that. And let's tidy up this filter here. And just take a moment to build. Well, it'll take a little while to build. But. So now we're actually doing something that's getting a little bit closer to this k-truss computation, by which I mean we're actually forming some triangles. We're getting some counts, some initial estimates, basically, of what's, well, for sure what's an upper bound on the level of k-truss that each of these edges will participate in. Though we need to actually make it be the correct answer, we need to repeat the process, essentially iterate the computation, so that an edge only gets points based on edges that are also present in the level that we're looking for. This is a bit vague, but I'll try to show you in just a moment algorithmically how we can go about doing this. All right, so we're seeing a bunch of stuff flow past. It's quite a bit slower, you might notice. So this will count up to about 800,000. So we're doing this triangle computation, not an intelligent triangle computation by any means. So we're using a slow algorithm. We're using differential data flow, which is not the tip-top way to go and find triangles in graphs, and it's just churning along. This is a really small graph. So this running time is seemingly large. We will, as part of working with this algorithm, fix up the triangle computation and make it go faster. But before we do that, I want to sketch out the actual k-truss algorithm, just to give you a sense for for what it looks like, how triangles connect toward larger goals, so that you don't have to scratch your head the whole time and wonder why we're doing what we're doing. Looks like it's even slowing down, which makes a little bit of sense if you think of as we start fleshing out the edges. We're going to have even more triangles to find. There's even more work to do because the changes are now to a graph that is itself a bit more complicated. That's super boring to watch. Let's check out some other stuff, like the activity monitor, which tells us how much memory is Graph's using. So Graph's is up at around 2 gigs now. This is for a graph that has, I think, yeah, just 800,000 edges in it. So, this would be just a few megabytes to write down the graph itself, which means we're clearly doing something more than just writing down the graph. And actually, let's talk about that while this runs. We don't really need to see how long this takes, but yeah, if we're okay, let's talk about what takes memory in this computation. Why are we up at, I guess it's bouncing around, but why would we be at 2 gigabytes? We loaded up at the beginning of our computation. We loaded up our graph. That was we said, it's just maybe a few megabytes. It's probably true. Like, no reason not to think that. We built some differential data, and nothing particularly complicated is happening. Is happening in here. Some of the differential data flow operators are stateful though, and as the computation runs, they will start to allocate and maintain some memory. And the only one that does in this picture at the moment, triangles we'll get in there, but the count operator, it's going to maintain memory proportional to the number of keys that it is counting. So these are edges, for example, right? We have we're maintaining a number for each edge, which was the number of triangles the edge participates in, and this operator will therefore keep an amount of state proportional to the number of edges in the graph. That was only 800,000, so that's not why we're having gigabytes of data. These other operators don't keep any state as they run. This is not doing anything. No. So down in our computation, we have a little bit of work going on here. Oh, wow, I've done something hilariously stupid, I think. Yeah, I've just talked at length about something which isn't even correct. Hold on, bear with me here. We are going to want to, these are not actually triangles, right? These are our candidate triangles. We haven't actually confirmed that they form actual triangles here, so let's fix that. A comma B comma C. This is the sort of thing you'd love to edit out in post, but I'm going to show you anyhow. So, right. So what we did is we formed the pairs AB and AC into ABC, and said, great, there's an edge from A to B and there's an edge from A to C. We didn't actually check to see if there was an edge from B to C, which we need to do by essentially doing another join with the edges relation here, a semi-join in this case, one that does not add in new values. And now this, wait, which one? Oh, right, semi-join, so sorry, this is now B comma C comma A. Great. This now has the potential to take a fair bit more memory, because the semi-join down here is actually going to be recording all of these pairs of triples, sorry, A, B, C. I was going to say pairs of edges, but triples, A, B, C, that are candidates for triangles. It's going to record all of them, because if the second input changed, we'd want to go and find, like, yeah, maybe a few more things have become triangles now. When you add an edge BC, we should find all of the ABCs that enable that. So we're writing down at this point, at this input over here, the first input to the semi-join, something that is substantially larger than the graph itself. Hopefully we'll see that this time, that it will, instead of wavering up in the 1 or 2 gigabyte range, maybe it'll actually will just blow out the memory on the laptop. This depends a lot on the degree distribution in the graph. So if there are nodes that have really high degree, and I think in this graph it was something that they have the stats for this actually in our paper, where they say things like, if I can remember, I can find the table. Great. So the Facebook graph, for example, has a max degree of 1,000. So some node out there is going to have a degree of 1,000. When we do this squaring, we're going to produce 1,000,000 candidates just from it. I don't like this at all. This is like faster. Amazing. Well, so this is faster. The only explanation I possibly have for this is that we were producing so many triples, A, B, C, before, that the act of counting them was surprisingly expensive. Now, I have no idea if this is actually the right answer or not, but we're going to go with it. We don't, unfortunately, as far as I can tell, these folks haven't, I don't know if they've made their data, their algorithms publicly available. I did not see any reference to that in their paper. So I don't actually have any ground truth to test, but we'll experience problems anyhow, and be delighted. Let's check out the memory footprint as this thing runs. This is really dumb. It's really dumb that by putting in more work here, this thing is supposed to spike up a lot, and actually it seems to have gone down because I did a better job of limiting the amount of crud that we were feeding through our counting. Unless there's some other mistake, actually. Let's check. There's a few things. Let's tidy up a few things here because we might have screwed these things up, or we haven't checked a few important things. So let's let collection. So I've been assuming that the edges are in a certain order. Maybe they're not. I mean, they are at the moment. But let's put that into place. So we've got source comma dest coming in, and if source less than dest, source comma dest, else dest comma source. Let's do distinct because if the graph has edges in both directions, we don't actually want that to count as two edges. Yeah. This was the only thing I was thinking might, if we had screwed this up, then we might be finding fewer, if there was a mix of in and out edges, but we were only using out edges to look for triangles, might find fewer things. Let's give this a whirl. And, anywho. So this is triangles. This is a bad version of triangles. We're going to want to improve it. I mean, to be honest, it seems like it's pretty good. At the moment, sorry, it's not actually good, but we should be able to make this fall over on larger graphs. It maintains a whole bunch of candidate triangles as input, and this can be obscenely large, even if it doesn't happen to be at this particular moment. So what I'd like to do next then is just to sketch out what the algorithm looks like for k-truss. It's very similar, but with some iteration going on it. And this does actually return a, I'll just put this in here as well. This actually does have the truss identifier as data rather than as a weight, so I thought I would just fix both of these to look more like that, so that we don't have two totally different bits of code here. So this, see if I can describe what this does in comments. Determines for each edge a number k such that the edge participates in at least k triangles with other edges with label k. So it's a bit of a recursive definition here. But yeah, the intent is that we're going to get out the largest number k we can find such that each edge participates in at least that many triangles with other edges that also participate in at least that many triangles with other edges that also blah, 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 blah. Now, one way that we can determine this is to start optimistically, start with the presumption that each of these edges has, let's say, like a really big one of these. So edge to edge, comma, maximum value for nodes here. So we're just gonna say like, oh, absolutely, you're super, man. You got lots of triangles, lots of great. But now we're gonna have to, before we're actually willing to report that outwards, we're gonna need to iteratively go and check. So we are going to take our initial guesses about these labelings and essentially try to confirm them. And what do I mean by confirm them? We are going to join together a bunch of edges to form triangles, sort of like we did up above, though it's going to break, but sort of like we did up above. And as we do this, we're going to keep track, as we form a triangle, we're going to keep track of the smallest label associated with that triangle. And then we're going to award points to each edge for each of these levels, and then we'll try to find the largest value of k. So when we look at all of the, how many level 1 triangles you participate, how many level 2, how many level 7, how many, all these things, we'll find the largest value that we can that satisfies you participated in at least k triangles of level k. So we've got our edges here. Let's rearrange them just a little bit so that they're easy to join. So let's do, I guess let's call these like labels or something like that. Let labels by source be labels.map. So it's currently source comma dist comma label, and we want to make that be something a bit more like source dist comma label, so that we can join them together. So for example, let's do labels by source dot join labels by source, which is going to produce a thing that actually let's do our filter step here now. So we're going to throw away any pairs that do not for which the B and the C are not properly ordered. So this will also just help us remember what this structure looks like. We've got an A and then a pair B comma label AB. We got a C comma label AC, and we want to keep this only if B is less than C. And now we want to restructure this so that we can join again and get that BC label out. So let's take A comma B comma label AB, comma C comma label AC. And what do we need? We need to have a B and a C. B and C. And then we want to have an A. And actually, we don't need to have both labels here. We can just keep them min. So let's do std comp min of label AB comma label BC. So this, we could keep all that detail if we wanted, but the sooner we collapse down, we project out information we don't need, the better, because keeping around all this crazy data is a problem. We're going to join this with labels. All right, labels is pairs of edge and a max value. Sorry, max value initially, but like the level that the edge exists at. And now we're going to want to do a map here down to, well, what are we going to do? Let's just put it in some sane order. So it's b comma c, then a comma libel. Let's call it libel a, and then a libel bc. And although we're going to do more in just a second, let's do a comma b comma c. So the triangle comma the comp min libel a comma libel bc. All right. So we've gotten as far now as saying we've got a triangle, and for that triangle we have the first level at which all of its edges exist, right? Which is helpful. This is going to tell us a bit about points that we should award to the edges A, B, and C. So let's actually do that now. One more prime, sorry. So we're going to flat map this up, sort of like we did up above, where we say A comma B comma C, and libel goes to, we're going to do back of A comma B comma libel, A comma C, libel, and B comma C comma libel. Now this for each of these keys, each of these edges, we're handing it essentially one point, saying you get one more triangle at this round, at this value of k, this label. So good for you. And each of these edges are possibly getting different labels at different different numbers of these with different values. And what we need to do, our very last thing we need to do, is integrate up all this information, pick out for each edge a edge, output, the largest value, largest label for which we actually have as many counts for that label as the value of the label itself. So I've written this once before, and I'm hoping it's correct. I'm going to try to do this on the spot. It's a non-trivial bit of logic, but not too bad. So our input is the edge is the key. So that's this part of the data we're seeing, and the input is a list, sorted list, sorted by label of label comma count. So we're going to do for label comma count in input dot iter dot, ready for this, rev. So we're going to go backwards. We're going to go from the large labels down, because essentially we're looking for the largest value where this is appropriate. And a fine way to do that is to start with the big ones and go down until we find something that works. In fact, we're going to want to let mute total equals 0. And every time we go through here, we're going to add the count to the total. Having added the count to the total, we might be in a situation where if total greater or equal to label, then we can do output.push of label comma 1, and then return. Like we're going to break out of the this loop, break out of the whole closure actually. And this is almost right, except we need one more thing that's basically the same up here. And why is that? So at this point coming in, sorry, not slightly different. So coming into this loop, okay, the very first time we come into the loop, total is going to be 0, nothing good's going to happen. We will increment total by our count, and indeed, yeah, this is a great time to check. If we've already got more representatives with this particular label or greater than the label itself, we're good to go. We should just push the label, return, walk away, and we're done. Now, we might come around that loop, and it's very possible. So at this point, we know that total not greater than or equal to previous label, but it could now be greater than or equal to the current label. Right? So we might have gotten our count up to 10, and we're now about to look at 7s, right? And we know that we have 10 labels, sorry, a count of 10 for some label strictly bigger than 10, because this didn't trigger previously. Which, you know, if we're actually in that situation, we should just go with whatever total is, right? Like if we know that we have 10 occurrences of some label greater than 10, 10's a great thing to go for, no matter what label is, right? We can only do this if total is bigger than label, because this is the thing that tells us that, you know, things are only going to get smaller than total from this point on. But I think this is right, and let's see what happens if we try. Let's just get back to doing cargo check, because there's probably going to be some structural issues here. 146, great. 146, we do not have a label BC, we have a label AC. That's totally true. No method named count exists. Yeah, well, we probably have to bring count in. That's true. Let's do that. No method iterate exists. Let's bring iterate in. Let's see what happens next time around. Join doesn't exist. Let's bring join in. It's all very silly. All right. 148 and 49 have the wrong shape. So 148 just came out of a join, and indeed joins don't produce triples, they produce pairs of the key and the pair of values. And that's true after this join as well. I think that's probably what I was complaining about. Let's see. Oh, I'm sorry, the map also needs to agree there. Map, great. No method named reduce, so we'll add in reduce. Oh yeah, okay. Now this is a bit of a mess. We just have to figure out what's going on here. So these things label, for example, the stuff in input is a reference to data. So it's like a reference to a label, in this case. We're iterating over it, which produces references to the things, and so it's a reference to a reference, this thing, here, reference to a reference to a thing. So we need to just do stuff like this. And we'll see if we can plus equals the count. No, we can't. We got to great. Let's tidy some of these things up, because we don't like Rust yelling at us. It's not that Rust yelling at us is so much of a problem, it's just that when it has something valuable to say, we do actually want to see that, because sometimes Rust is right. Alright, so that doesn't matter. We can just, another thing you can do is just put an underscore as the only thing in there, and that really cleans up some of the noise. Alright, so we're not actually calling truss, let's call truss. Where are we? Truss. Truss. Okay, now triangle is never called. Let's build and run this, and if I remember correctly, this will build. It'll take a little while, and then it will do nothing good at all. Let's see. All right, it's up and running. If you recall, nothing very much happens at the beginning. Oh no, sorry. I forgot if we turned on this batching stuff or not. No idea what's going on then. Sorry, I'm gonna check to see what arguments we ran it with. True. So we did ask it to do time rounding of times. I mean, it's totally possible that we've massively screwed something up in our computation. We do have inspect set to true, I think. So ideally, we should be seeing some output if there were output to see. And probably instead we've just screwed something up in our computation. We'll have the privilege of debugging that. And it's actually doing work. So it's not just casually ignoring lots of stuff. It is exercising itself quite heavily to do nothing in particular. But we are seeing no output. So like I'm pretty sure that this is not right at the moment. And we'll need to just double check. Yeah, we get the counts and there. We should, if anything is moving fast, we should be seeing it here. So we'll put in some more inspects in just a moment. It looks like it's almost about ready to finish there, so great. Neat. All right. The fact that it ran to completion should, in some amount of time, should not in any way impress you, because we don't seem to have actually done anything particularly good. Let's do some pretty casual printy prints here. So let's take labels and grab the second field, the label field. Let's consolidate that and then inspect it. So this should show us as we're actually iterating in our iterative computation what's going on. Right? Probably, right, we're seeing a whole bunch of really big values come in, and then possibly we're immediately seeing them all get deleted for some reason. Like we have totally failed for possibly to have actually put together any triangles that have any particular values. I'm just reading through this as we go to try to get a sense for, is there anything patently obvious that we might have screwed up. We are adding to our total as we go around. That would be a common screw up. I have a version of this that works somewhere else on my computer, by the way, so I can always just cheat and go find it. But probably good if we look at this together to try to figure out what's gone wrong. Filtering should still let half of these things go through, and the ones that are in the right order. When we do our join with labels, we put BC in the right order from small to large, so we should absolutely be finding things in labels. These edges that we reduce out are also in the right order, so yeah, I'm thinking, well, I don't see it yet, but and with the runtime set to true, we should be dumping legit data in there every however many, 10,000, 1,000. All right, so okay, this is right. So something is absolutely going wrong here. So we're seeing a lot of people come in with the max value, and then in the very next iteration, so whatever round 20 it is, initially 1,000 people with edges with this value, and then in the very next iteration, nope, we delete all of them. So for some reason, actually, sorry, that might be premature, but let's run this for a little bit. For some reason, that reason might be there aren't enough edges yet, but for some reason we are happily just, in fact, let's crank this up by just a little bit so we don't have to Yeah, so we're basically discovering nothing as we go. Not even, so a few iterative rounds of little bits of collapse. Um, we have failed to do our triangle math here because even if things decay over time or something like this, we're starting out saying like, no, everyone's valid. Let's actually just what this should have been. Let's actually just go and compute for everyone who has this max value coming in, number of triangles that you participate in. And this should have been, you would have thought here, should have been firing. So let's just make this be really noisy. But geez, how do I try to figure out a good way to debug this without spraying the screen? So what I wanted to see was to confirm, right? Oh, surely we're seeing some label with some exciting count, which will cause us to actually go and do a thing. And I wonder if we possibly need to. I wonder if we possibly need to, at the end here, maybe the thing that I've forgotten is if total greater than 0, output.push total, 1. What do you think about that? So if we get to the end of this, and we haven't actually seen a label that we have accumulated to more than, so like we get to the end of this and our total is 3. But all of our labels were max value, which is still put 3 as our output, right? Like we're still, 3 is still a total legit number. And if we see 0, we probably shouldn't bother to mention it. We should probably just, die. I don't know, fall on our sword. I don't know. Actually, let's just, that's a silly optimization. I bet that's the problem, because it's easy for me to bet that's the problem. But I think that was definitely a problem, was that for sure the first time through, the only label we see is the max value, and this code would never push anything into the output, because nothing will ever be bigger than that max value. And we kind of wanted to fall around, in a sense, and do that first test again for the label 0 with a 0 count. So let's let this build for a little while and see what it does. Ooh, it's running, and it is printing a lot of data that we probably want to tidy up, because we're not going to make any sense of this. Get back here. But we did see, I don't know if you noticed, there was a bunch of really tasty stuff flowing past, which is not just immediate deletion of those really large labels. The really large labels were being deleted, of course, because they're not the correct answer, and we're not going to end up there. But then there was a lot more churn and variety and variation. So probably more likely to be correct, not necessarily correct, but moving in the correct direction. All right, now we're up and running. What's going on here? Scene. So these are um, levels, k-core level, or sorry, k-truss levels that we actually saw changes for. And they're sort of up in the, I guess, 12s, 10s and 12s. Let's check 36 is apparently the maximum value. That probably happens a little bit later on in the computation, even if we're getting it correct. And let's check another thing, because I know that this goes wrong at some point. Oh, not yet. Cool. The memory utilization is under control. So we're basically watching, this slowly go by. The number 10,000 is actually a good number, a good round step size to use, because when they go and do their evaluation, that's what they used. They basically load up the entire graph and then go, all but 10,000 edges, and then see how long does it take to do the last 10,000. Which actually, we can leap to that actually by doing the following. Projects, data sets, out, Facebook. So if we set our round size to be everything except, so this minus 10,000, which is just that. And we can, it'll do the first, all but 10,000, report a time for that. That'll probably take quite a while. And then do the last 10,000 and tell us how long that took. And this was the sort of experiment that I was doing before that went sideways with memory utilization. But let's see what happens. There's a good reason that it should go sideways with memory utilization, but let's give it a chance. If you recall, this is computing triangles and doing a bunch of basically just like not being very clever about how it goes and does things. Triangle computation is something that clever people, have thought a fair bit about and have better algorithms than just doing a few joins together. So at the very least, we can make that go a little bit faster, and I think there's some related structural issues in our computation that we'll be able to improve. But this is grinding away. To be honest, I wish I had more visibility into what was happening around bottom. You know what I'm going to do? I'm sorry, this is going to annoy you, but I'm going to put this back in place so that we can actually watch it develop iteration by iteration. So we'll get all 800,000-ish edges loaded in, and then it will start to show us as it goes through the iterative rounds of computation of essentially lowering the labels for each of the edges, what sorts of changes are underway, and it'll give us a bit of a sense for how promptly are we moving through the space of all labels. And we might have, everything we were looking at there, we might have just been sitting at the very first round of iteration, and we're going to be thinking forever, or we might have been happily churning away and getting closer to the end. And this will just give us a bit more ability to watch, see what happens on our screen. So this first bit is telling us that all of those edges that we added in, plus 1, looks like, who knows, decided that they wanted to be at the max value, which is right, that's where we started them. We've now done one iteration, and everyone agrees that was the wrong value. That max one, not so good. And there's a bit of a smear now across different other values, depending on how many edges, how many triangles each of the edges participated in. You can sort of see that, yeah, there's quite a lot of them with smaller counts, but out in the limits, there's a fair chunk. And now we could go around again with much more rich information about different labels for different triangles, and try to amend the computation. And this is definitely one of the places where we start to take some more memory and do a bit of work, because if we look at the code, where we're computing our triangles, which is sort of roughly these lines in here, we're not just computing triangles, we're also computing triangles with a bit of a history of the labels as they change. So not only are we doing the work of joining some edges together, but each edge comes with not only some label information, but some historical label information. This looks like we expect to see, this is a good point, we expect to see a lot of negations, right, because these things only get smaller, these labels. So folks generally are going to migrate from higher numbers to lower numbers as a result of iteration. No one, in no round of iteration will, should we, unless there's a bug, in no round of iteration should we see someone increase their label. There's this sort of a built-in monotonicity property here, which is helpful for keeping your sanity when you think about these things. That as labels get smaller, everyone else's labels can only get smaller too, and that's one of the reasons that we're comfortable running a fixed point computation here, which is that we're pretty sure that we're going to terminate. And we're converging downwards. If you recall, we're not supposed to find anything bigger than 36, I think, in the end. So all of these numbers up here that we're deleting out, yeah, it's good that we're getting rid of them, because they're definitely not supposed to be there. And masked by some of these, like, we might be deleting 326 occurrences of label 50. Probably what's actually going on is that we're deleting slightly more of them, and we're actually gaining a few that have migrated from some higher number down. So, but another thing you can see too is that there's also fewer total changes. Right? So our iterative computation is stabilizing a little bit. Obviously, it has to stop at some point, because we can only, there's a limit. Everyone can't go any lower than 0. And so we will eventually, the set of changes will have to get smaller, and it ends up being 0. And ideally, along the way, how we go memory-wise? Oh yeah, we're getting some more memory use there. Ideally, things speed up as we go on account of these changes become sparser and sparser, and the fewer changes there are, the less work we'll do. That's great. But unfortunately, we just sort of sit and wait for it at the moment. And then we get to see at the very end what the last 10,000 do, whether that is a slow process or a speedy process or what. Fewer and fewer changes. We're getting closer to the 36, was it? We're not likely to actually be able to tell from these diffs whether we see as 36 in the output, just because we're only seeing changes here. So if someone's sitting at 36, they don't get mentioned anymore. And to figure out what the final value of 36 would have been, we would have had to have been recording all of them. And, possibly we'll see it in the, ooh, it's going fast. All right. Oops. So this is, we're now in the 10,000 updates. Let's check on the memory use here. 8 gigabytes, that's quite a lot. So we're now going in, what can I see here? We're now going in with our last 10,000. I'm not really sure why that number is slightly off, but and apparently fairly quickly they concluded, nope, that was wrong, which makes sense because they, whatever their inputs are, this wasn't right. And now we're doing, it seems like quite a bit more work. Okay, oh yeah, good point. This is in that first round, the only thing that changed was these edges themselves had not so much to talk about. And arguably, the edges might have contributed some really high labels to some other people, but that didn't change any of their opinions about things because getting through, you're not going to pick up that label. But now we're starting to see knock-on consequences where throughout the graph, there are these annoying little changes you can see here where people are sort of shimmying around from one level to another because these 10,000 edges, not very many edges, changed a count by 1 or 2 in some place, which caused, generally it's going to be, I'm not really sure here, I would say generally it's going to be only increasing the labels associated with things. Though the math in differential data flow is weird, so what this could very easily mean, although we're seeing a subtraction from 29, it could very well mean that 229, that in a previous round, yeah, for example. So this just means we got to 229 one round earlier than before, and we had to subtract away a occurrence of it in the second round because it's already been reached in the first round, and we have to, all the numbers need to still add up to this. I don't know. It's getting your head around exactly what differential data flow is doing is a bit of a mess. And memory is still big. So interestingly, we haven't really done that many changes, and yet it's taken a bunch of time. And some of that's probably reasonable. Like some of this is due to the fact that these few changes still percolate all throughout our graph and cause people to have to reevaluate things. And reevaluating their place in life is more complicated than just taking a +1 or a -1. They need to reassess what level should I exist at. I better tell all my friends that I changed a little bit. All of them need to reconsider and say, well, you know, you had 20 odd neighbors, and you know, it's maybe like even if 10% of them need to change their mind, that's just going to grow throughout the graph for a little while. But here it seems to be speeding up a little bit, which is good. And look at the time, and this is almost certainly going to be like a few minutes. And then we can look at how long it took the other folks to do their computation and see that the other folks, all right. So, okay, something possibly is wrong because we only see a 34. We don't actually see a 36 like they report. So it's possible that our algorithm is screwed up, actually. Yeah, or theirs is, but probably ours. And time-wise, this is 545 seconds. Let's see if we can track down when we started this whole thing. Not started, but like when we... So there's a gap from 326, which is when we were just about ready to take on the last 10,000. And we spike up to 500 something, even bigger. So 220-ish seconds, that's 3.5 minutes or something like that. Which is for sure a lot bigger than, ready, check this out, how long they took, which was 0.23 seconds to do that fix. prior work, this number here would have taken maybe 26 seconds. So we are at the moment some 10x off of slower than prior work, and nowhere close to. So we are we're 3 orders of magnitude slower than this new paper, which is cool. I mean, we've learned a thing that like doing total simple simplest possible version of this is not the what's the right way to say this? The paper is indeed not just a triviality. Like it doesn't get you the numbers that would just result from typing into a differential data flow. But we can start now to think a little bit about how might we improve our performance a little bit. In particular, we could improve the triangle computation a bit. And there's a few different ways to improve that we could talk through. And it's not entirely clear that's going to make, that's really the source of all of the problems. But we can talk through, what's the hard work that we're actually doing in here. So, right, for example, like the reduce, hard to know if that's really actually a problem, in that we are for each edge going through a few different values. Maybe, if there weren't a lot of different values attributed to an edge, this isn't super expensive. Though if they're changing a lot, even in uninteresting and unimportant ways, that's relevant, right? Like if let's say you're at number 37, sorry, you can't be at 37 because that's what we said, but you're at label 30, so you got 30 triangles you participate in with labels bigger than 30, and these jerks keep coming around saying like, hey, I'm at level 3. Here's one more point for you. Like, I don't care. Screw away. And we're still gonna, because we're not super smart here, we're still gonna go and reevaluate this logic for each of those sorts of changes. So that's possibly one source of stupidity too. I mean, the output won't change, so like that will suppress the change propagation. We won't do any more work afterwards for it, but we'll still redo the work. We'll even if we could, in principle, structurally look at our current state and say like, no, we don't care. Like we literally don't care when you show up with a plus, with a label of 3, and we're already at 30. Beat it. The other thing that's going on is the triangle computation up here, which is being done relatively inefficiently. And I thought I would try to fix that because we've done some triangle computation a few different ways in a few different places. And it's possible that we could be smarter here. So the trick we have, let's see, we have 2 things. I'm just sort of thinking out loud now. We've got 2 types of tasks we need to do here, and we might want to break them apart. One of them is determine triangles. Another is, for each triangle, assign these min labels to the triangles. And we're doing both at the same time. We're sort of discovering the triangles and also maintaining the min labels, but maybe we would prefer to actually break these things apart so that we compute triangles once, essentially. And then we do the work of maintaining, essentially just joining in the labels. That we're maintaining a map. This sort of labels thing up here is a map from edge to labels. And we could, having formed each triangle, just go and do some joins to get all three labels. Let's see how that works. I'm sort of curious about that. So let's do let triangles equal. And I'm just going to steal this code up here for the start. This still isn't even the best way to compute triangles, so this will be another thing that we'll want to fix. But for the moment, let's do this. Let's bring in triangles here. Let triangles equals so bring it into scope. We're not going to need labels by source anymore. We're going to a bunch of this code is going to vanish. Um, we can leave the label inspecting code around just so that we don't have to stare at nothing for 10 minutes. We brought our triangles in, and our triangles are triples probably. No, they're BCA things. Weird. All right. And what we're going to want to do is repeatedly, in the most naive form, repeatedly join with each of AB, AC, and BC to get each of the labels that are attached to each of the edges. So let's just start doing that. Let's do put these together so that I can comment them out in the block later. Triangles dot join labels. Let's do join map labels. So this is B comma C comma A. No, B comma C. The triangle also had an A with it, and we have a LBL, an LBL. And we're going to produce the next thing to join with, which let's just say is A comma B comma C comma label. Oops, guess that's not properly. So we stash the BC label in there, and we don't need to remember which labels correspond to which edges. We're just going to keep minimizing all of them. So this is now A comma B comma, and then we've got two things here. We've got a C and a global 1. We have a global 2. And we're going to want to produce, I believe, A comma C comma B comma stud min global 1 comma global 2. Then join map again with labels, and we have now A comma C and B comma global 1. We have our final global. And for the moment, let's just produce A comma B comma C and a stud comp min global 1 comma global 2. At this point, this is when we're going to want to see, we've done our filtering, we've done all of our stuff there. This is the point at which we're going to want to dive in, essentially do this code. So flat map from ABC and the labels to these dealies here, and then basically just exactly as before. So this is the same logic, meant to be at least the same, produce the same collection as before, but rather than try to assemble what could in principle be a changing edge set as we go and all these weird. Now we're going to compute the triangles once, and then do a bunch of lookups into the labels. This isn't going to make things free necessarily. Free meaning we're still doing a bunch of work here proportional to the triangles, but maybe this is a little simpler. Let's see. Let's see if it builds. It does not build. We need to make this be a reference. Great. All right, this will take a little while to build. Talking through this, although triangles doesn't change in the context of this iterative computation, the labels will, and in particular, the output of this result is going to look like triangles. It's got the A's and the B's and the C's and some changing labels. And that means that we're going to, as we move forward into each of these subsequent joins, the inputs are going to be proportional to the number of triangles out there, because we're going to, for each triangle, hopefully we found the label for it, proportional to the number of triangles, and then scaled up a bit by the amount of variation that their labels undergo. So we're still doing a fair bit of work here. This is going to be an amount of work that depends on more than just the number of triangles plus the amount of change in the labels, which is what you might have thought. Right? If you think of these labels as oh, it's a hash map, man, just look up the edges and man, we're good. That'd be nice, and we're going to try to get there. There is a way that you can do this in differential data flow. A bit more principled than just saying hash map and doing things. But yeah, at the moment we're still stashing a fair bit more state than we might think, stuff proportional to the product of triangles and the change volume for their labels. But we don't have an intermediate state that depends on the squares of the degrees like we did in the previous version. Right? Like when we were doing the triangle computation, at this moment here, one of our inputs has size proportional to the square of the degrees. It would be too bad if we had, as we do down here, something proportional to the square of the degrees times the change in their labels. We sort of restricted that down to actual triangles. I'm not sure what we're going to watch now. We're going to watch the a little bit of the development of this, I suppose. This is going to take a little bit of time, and I suppose I can edit this in post if it's a little bit too slow and boring. Or maybe we'll see early on, like if the memory might spike because we've got a few joins now, so we're doing triangles by labels a few times, right? Twice at least. Triangles once, and triangles by labels twice. Now we're already in the third iteration, though. That seems promising. Or I seem to remember this took forever and a day before. We'll have to see if we get the same answer. Well, already this is looking a little bit better, actually. Well, sorry, it's looking faster. Whether it's looking correcter is a different thing entirely. I think we should see, I mean, we've ditched the data already, but I think we should see iteration by iteration the same numbers because unless there's some subtleties that I'm missing. The evolution of the label collection should still be the same iteration by iteration. All right. Well, who knows? But that was clearly a lot faster. Who knows if it's still correct? We're still seeing out to 34, which is the same thing we saw last time. Not necessarily correct. Now we're going in for our 10,000 change, which is surprisingly slow at the beginning. But looks like it's picking up. Time to beat is like 26 seconds or something like that for the previous generation algorithm, which would put us only 100x slower than the current algorithm, or the algorithm of the paper. Well, here we go. Boom. All right. 155 thingy. So about 50 seconds to go from there to here, which is definitely slower than by about a factor of 2 now, not a factor of 10. So, aren't we very clever? Than the previous state-of-the-art. Just for kicks, because, let's try with 2 cores. See if we can get that 2x back. This is arguably one nice feature of doing a thing in something like differential data flow, as opposed to a bespoke algorithm, is that you get sort of for free parallelization, which, especially in this type of computation, can be really helpful because obviously we're doing a lot of work, right? Like this is not 150 seconds of waiting for web requests to go and hit some other continent. I mean, like this is actual compute that we're grinding away pretty heavily on, and a second core could plausibly be useful here. Or not. I mean, who really knows? But let's see. So it was, I think, 106 seconds to get to the end of the first iteration, or first. Oh, we're done? Wait, really? Did I fuck something up? Oh, I bet I did. I bet this is silly, but I think we have to divide this number by 2 because each of the 2 workers is pulling in this much data. So let's do, this is a bad experiment, but let's do 400,000. So it's a bad, actually, sorry, bad experiment in that we're not computing exactly the same thing. It's all, this is weird and complicated, and we can fix it, but we'd have to recompile the program. So, but we'll fix it for our next. Actually, let's do that now while it's running. So what we really wanted to do was when we picked out the batch size up here, we probably should do the following: let batch size equals batch size divided by worker.peters. So we're going to scale down the size of the batch by the number of people there, so that when we multiply by worker.peters, it goes up. But we also want to add if batch size mod worker.peers is greater than worker.index. What the heck you're probably saying? So if there's some leftover, so this will, when we divide by worker.peers, we'll round down. So if we multiply by worker.peers again, we don't get quite to batch size. If we get actually to batch size, we need to have some of the workers actually add 1 more in. And you might say, dude, why waste our time with that? But if we actually want the same answer to come out, and sometimes we do, this is important. If we want to do batch size 1, this is also important, right? Like batch size 1 and then more than 1 worker really screws this up. We never make any progress. How far have we already? All right, so we had 72 seconds instead of 106, I think. Okay, now it was 72 up to, this is still 50 seconds. So interestingly, that didn't really seem to help too much in the updated case. I don't know why that is. It's not for the normal reason that it doesn't help too much in incremental update cases. Oh, I see. Maybe we're doing twice as much work, basically. Not twice as much, but if that number should have been more like 10,000. So we were doing 16,000 edge changes instead of 10,000. Maybe that's what that's about. I don't know. This isn't very scientific at the moment, but all right. So let's absolutely just delete all this crap here. No one wants that. But there's still some major sources of inefficiency here. So let me take a bit of a breath and talk through what those are. Now, the way join and semi-join works in differential data flow is both of the inputs are captured and maintained so that changes to either input can be immediately looked up in the other input. It's called a streaming hash join, usually is the term, but you don't even have to use hash maps. But both inputs are maintained so that any input on any new data on either input can be indexed into the other input, and we find matching records. Totally same thing to do, especially if you're only joining 2 things. That's basically the implementation you need to have. But in a more complicated multi-way join, such as we have going on here, and in fact, such as we have going on up here, it's a bit trickier. And the reason is we don't necessarily want to maintain all of these copies of all the triangles of all the crud going on here. Right, so we're keeping track of we're trying to produce A, B, C, label, which we produce if there's a triangle A, B, C, and also label A, I don't know how to describe, like min label. So we're actually uh, so we've got several. I'm essentially writing out the join that we're doing. So we, starting from triangles, we also join with label ABC, label AC, label BC, taking the minimum labels as the output. And we have planned it like this. We sort of said, put some parens around these first two, then put some parens around the second two, and plan them out as binary joins, but we don't have to. The thing that we can do next, which is sort of cool, is the following. This is part of the, I'm familiar with this, part of the dogs sub-project in differential data flow, so named for these three dogs. So those are the mascots there. And it's an implementation of something that in the database community is called delta joins. So what do I mean by that? So what we actually need to produce here, we've written it as a computation that determines a collection, A, B, C, and some labels. But what we actually need to do is write a delta rule. So a thing that tells us how to change A, B, C in the label, potentially as a function of changes to these inputs. And we had one plan, was, yeah, we'll make a bunch of binary joins, each of whom respond correctly to changes in their inputs. That should produce the correct changes in the outputs. And so we could totally say that this should be equal to the delta rule applied to this join. It's a binary join operator where we supply changes to triangles and changes to labels into one join. The changes that come out of there, we match up with the changes to labels, changes that come out of that join, blah, blah, blah. But there's a better way, actually, turns out. Well, there's a better, I don't know, but a different way, which is to plan different data flows for each of the 4 inputs that come on here. So let me describe what I mean by that. So we could actually describe the changes that we need to produce as output as 4 different types of change. So one of the changes is due to triangles changing, for example. So we might do delta of triangles of A, B, C. And if only triangles changed, let's just imagine the other relations were held constant. If only triangles changed, then we just need to look up the associated label in AB, AC, and BC. So if someone added one new triangle but didn't change any labels, we just go look it up, and we take them in, right? Tap that in. Similarly, what happens if just this label changed? And this is going to be a bit harder to believe, but bear with me. So let's imagine that just that changed. Then the only thing we need to update at this point is they have a different length. Why is that? Did I screw something up? I'm surprised that they're off by 1 character here, but oh, triangle. There we go. If someone shows us a change to only these labels here, I don't know why these other labels haven't changed, but if it were to only these labels, we would only need to go and join with the current contents of triangles, labels, and label. This is because in the relational algebra, the relational join distributes. So if we had a change, plus change, we could apply distributivity to say, well, this is equal to what you used to be equal to, plus whatever the change was. So distributivity of the relational algebra means that that's actually equal to the old query of label plus change, label, label. And we're going to use that rule repeatedly to undistribute hypothetical changes for each of the input relations and write different data flows that describe how they should work. In particular, if we do AC and BC, they're going to look very similar, except I'll just write them out for you. They're just going to look very similar, except that when a change happens to AC, we need to consult labels AB and BC and triangle ABC. And when a change happens for BC, we consult these oops, sorry, BC. And the reason we do this seems like we've just made everything much more complicated. We've made things a little bit more complicated for sure. But the reason we do this is because we are now effectively just doing a lookup into triangle. We do not anymore need to, because we're writing out the delta rule here, we do not anymore need to respond to changes in triangles in this data flow. Right, so that makes this much simpler data flow to implement. The changes stream in, they stream past this relation, past this relation, past this relation, but we don't need to write them down. Right? So that we don't need to write down the changes as they go past, which is unlike the case for the binary joins where we had to write down everything that went past so that a change to the other input could resolve things correctly. So one of the things that we're going to do is to describe our label lookups as these 4 delta rules rather than as all of these joins here. And the intent, at least, is that we're going to skip the state maintenance that is proportional to the triangles multiplied by the rate at which they change. It should instead be an amount of state, at least, that's proportional to the triangles plus the labels. We will move about as much data as before between the stages, but we won't spend nearly as much time maintaining it in indexed representation. And in principle, I suppose, when we do lookups also, we won't be doing lookups into large amounts of complicated state, but rather following a sequence of lookups through smaller state. Right? So for example, like if label BC had changed, that would have triggered like all the way back in the very last, actually I don't know which one it would have been. Sorry, BC was the very first one we did because we had our labels and our triangles in some weird order. When AC, the very last thing that changed, in our prior model here, we'd be doing a lookup based on AC into a list of all the triangles and all the labels associated with all those things, and a pretty big amount of state. And instead what we're saying here is, no, when AC changes, here, join it with triangles, join it with the other labels, once, twice, and you're done. So each of these lookups are into something that's only as big as triangles, only as big as labels, which is proportional to the keyed by edges, and then depending a bit on how much they change. I do that twice. So not so bad, really. Yeah, great. So we could write that. Let's take a moment. I just want to talk through the other change we could make. The other change we can make is that triangles are being computed in a stupid way. This is a very primitive way to go and compute triangles. I don't have a great readout at the moment on how long we're spending computing triangles versus iterating. We could figure that out, I suppose, because once the computation gets iterating, triangles aren't being recomputed. So any time that we see that's in the iteration time is down here. The triangles themselves optimizing that computation. I don't know, maybe it's not so important actually. Let's not do it at the moment. We'll put it to do. This is, though, an example of a computation that can take asymptotically more time written this way than needed, because when we're taking those degree 1,000 people and producing 1 million candidate triangles. Let's look at these stats again in this paper. So we've got someone who's got max degree 1 million, and as it turns out, we can see, though, not necessarily the case, there's only 3 odd million things in here. So we're actually, we're going to be looking at millions of candidates just because of the way we choose to square the degree, and that's a bit mental. And there are smarter algorithms instead that say, rather than go and produce all of these pairs, the rough algorithm is, take each edge AB and then propose C's using edges from the A or B with lower degree. So if A has degree 1,000 and B has degree 5, great, have B propose the C's that we're going to talk about, and then have A double check them. instead of having A propose 1,000 and then B say that like no, all of these are crap except for 5. Anyway, let's not do that at the moment. Let's instead try out the dogs stuff. That's actually, it's just in the differential repo, so I'm going to open it up and we're going to look at the code together because I've forgotten a little bit about what that looks like. Examples, and I think dogs. Oh no, let's do delta query. It's a little simpler. So this is a program. It's 100-ish lines, and it goes and does triangle computation. I want to say. Looks like it. Yeah, it's gonna do triangle computation. And there's some weird stuff here. You can see the alt-noi stuff. I'll explain what's going on here. This is a clever way to share some state between operators. But the rough idea is going to be that we have a query here. This is triangles, but we'll apply the same types of reasoning to our own query for label assignment. E1, E2, okay. We're pretending, for sanity's sake, that these are different relations, E1, E2, and E3, so that we don't get confused when we talk about which rules we're writing at any particular point in time, though in reality they're probably all going to be exactly the same. So what we end up writing, all the way down here, is how does the query queue change when there's a change to E1? Yeah, which is going to be the stream of E1 changes joined with some E2 changes, joined with some E3 changes. We're going to write these out for our triangles and labels 1, 2, and 3, essentially. So what's going on? What's going on in each of these? I'm just going to talk you through this, and then hopefully we'll just be able to type some stuff, and we'll be all set. So there's a few methods that are introduced in the dogs repo. 2 of them you can see here, propose and validate. There's another one, count, that you don't need unless you're doing worst case optimal join stuff, but we're not going to do that for the moment. So what does propose do? Propose takes a stream of changes. These changes, for what it's worth, are just the stream of edge changes. So we're using those for DE1, DE2, and DE3. Takes a stream of changes, and it takes an index. I'll have to tell you where this came from. But this is essentially an indexed form of E2, keyed the appropriate way. So forward, meaning so keyed from B to C, which is useful because we show up with a B, and we want to look into the edges and find, okay, where does that B go to? In other settings, we might want to go backwards. You can sort of see in changes too, we have some reverse stuff. Don't worry about that for the moment. Yeah, so forward key, meaning we're going to go from B to C. We're not doing an intersection with the pair of B and C. Some of these complexities won't show up in our case because we aren't doing nearly as complicated a join. And then key 2, which essentially tells us when we're presented with an A and a B in that input stream, what field should we use for our key? Could have been A, right? This could have been A comma C here. We could have done things in a different order. But no, actually we want to pull out the second field. So this needs to be a closure telling us how to go from the input changes into the keys we want to use in this indexed over here. And my guess is that what we want to do is keep our labels indexed from edge to label. That's going to be a pretty common sort of thing that we want to do. Because as triangles and as all sorts of things spill around, we're basically just looking things up by edges in our computation over here. So this join is never, we don't drive it by saying like, hey, I've got a label in mind, can you find me some edges? We never really say that. And the other weird thing, I suppose, is the noi versus alt. So you see some noise here and some alts here. So what's that about? Now, we're going to have this problem. We're going to have to deal with this as well. The problem is that since these are actually the same relation, when a change happens, if a change happens to the edge relation, and we process it, just following these rules just as written, we're going to over-derive changes. So change E1 will come in and say, wow, look, let me look at E2. And if we look at E2, well, if we look at E2 as it exists just after the change, we might trigger the same output from a change in E1 finding a new record, the same, finding itself even in E2, as we would in this rule down here, where changes to E2 come along and bump into the now current version of E1. We could in principle fix this by saying you don't get to look at the current version of E2, you look at the slightly old version of E2, but then we'll miss, in both of these cases, change to E1 that's concurrent with a meaningful change to E2. Like, let's say I literally just add 3 edges to my edge relation that form a triangle. We want to see the E1 change and find the corresponding E2 and E3 edges, because it is correct for us to find them and produce them as output. But if we do exactly the same thing down here, we'll find the triangle again, and that's just wrong. So what happens then is, as we use these indices, we use a slightly different timestamp type, which allows us to flag every change as either old or new, alt or neu. This is back when I was in Germany. Switzerland, the same. So this is saying that when changes come in E1 and join with E2, we should use the new version of E2, the one containing changes at the corresponding time in E1. Which is good, we want to find those. However, when we come into this join down here, we join E2 with the old version of E1, alt, which just means that if we find 2 diffs with the same timestamp, they don't match. Whereas up here, 2 folks with the same timestamp should be like, yeah, great, you're less or equal to me. We're gonna count this. These times are just an infinitesimal unit. This is weird to say, but an infinitesimal unit ahead of these changes, so that they are not actually seen. They're not present when E2 shows up. And that's a bit weird. But that's the thing. And great. So we do that just to be careful to make sure that we don't overderive things. In some computations, it doesn't even matter. Like this, it matters if we're counting triangles, but if we're just trying to determine the set of triangles, it's not a big deal. It matters in differential data flow because actually we are counting triangles all over the place. Like when we're doing changes, pluses and minuses of triangle counts, you don't want to accidentally subtract out 3 triangles just because all 3 edges went away at the same time. So let's try that. We'll have to explain what each of these things does. These are arrangements, which is ways of structuring our data so that they can be reused carefully. But what do we need? Well, we need to probably grab some dogs references here. References. Let's go stuff dogs. Yeah, I'm really sorry. So, and we'll also want these methods. Where did we get those from? These folks here. Great. All right. Now, what I think we're going to want to do is we're going to want to do let labels by edge be labels dot arrange by key. This is something that basically just says go and make an arrangement. Arrangement is a physical representation of the same collection. So whereas the data were just pairs of edge and label, this is now going to force them into a representation that actually keeps them indexed that way and allows us to use and reuse that physical representation of the data. Great. Just looking at this stuff over here, we're probably going to need to have triangles arranged a few different ways. Right? So triangles, this is just me looking ahead, but when someone comes in and says, I've got to change to the AB label, we're going to say, oh, geez, I hope we have triangles indexed by the first 2 variables. We'll need indexed by the first and third, and by the second and third. And these are all different ways of representing the data, so we're going to need to carefully go into that too. So let's triangles AB gets triangles dot map. This is A comma B comma C, A comma B comma C dot arrange by key. And we'll want that 3 times. AB, AC, and BC. And this is basically what this is saying. So we actually need, when I said we look up things in triangles, we need them indexed a few different ways. Conceptually, it's easy to think about like, oh yeah, just look it up in triangles, but each of these changes has 3 different ways to look things up. Super, and now we're going to be replacing this hunk of code here. I'm going to comment that out for a moment. And to do it, we need to do a weird thing that I sort of glossed over up here, which is we need to enter into a new subscope. Right? Kind of cool. It's not triangles, it's going to be, I don't know, kind of is, it's not triangles, but it's going to be counts of, well, it's, no, I'm sorry, it's going to be triangles, basically. It's going to be these things here. So let's just, I guess we leave it called triangles. We don't need to reuse the name triangles. Jeez, I feel bad. Triangle labels. There we go. We don't have a scope here, so let's do labels dot scope. And what's going on here? So we are going into a new subscope where we are able to delete this, wrap different arrangements with alt and noi modifiers without making second copies of those arrangements. So we're going to do things like, I'm just going to write a lot of these things out. Let labels by edge alt equals, and I'm just going to steal these things. Labels by edge, enter at inner. Ooh, what is inner actually? Oh, it's inner scope. Okay. I'm trying to think. It's not a. This isn't like this thing. It's not a collection. It's a scope. So we'll get 2 of these alt and noi. Alt and noi. And what this does is it gives us access to labels by edge, both essentially just before and just after various moments, so that we can pick an order to use to logically execute these joins without putting in duplicate sorts of things. Let's just bring the triangles in. I don't think we need to have the triangles be alted and noid up. We could if we wanted to, but we could also just essentially say this rule fires first. So what we're going to logically do is put an order on the order in which these rules fire even under simultaneous updates. And if we say that triangles updates first, then no one ever needs anything except the new forms of triangles. So that's great. So we'll just bring in each of those triangles. Triangles underscore equals, yeah, triangles underscore dot enter. Enter will put a default default timestamp on, which should be alt, I believe. It should let us see what we want to see. I said before that something that wasn't correct, which was that this role would be able to see the changes in E2. I've actually written it the other way around, so that this role, by using the noise, does not get to see. So noi is the time that is nudged a bit further forward, and so concurrent changes to E1 and E2 will not fire in this role. They'll have to wait until this role down here, where we use alt and alt for concurrent changes to actually be fired. So if anyone is paying very good attention, first of all, amazing, love you, but that might be why you were confused about what I just said. AB, AC, BC. Now, what's going on here is that we... What? Why did I do that? That's silly. Sorry, I want to do that in here. So we brought in each of these arrangements from the outside world, outside scope. We've not actually arranged any new data, though. We just basically wrapped a little bit of code around them that says, like, when you want to look at my timestamp, actually you get to look at alt of that timestamp, which has some cost, but isn't especially tragic. If we want to ignore that, what we could in principle do is bring these triangles in here and arrange them inside, and that would, since we're not planning on reusing these arrangements anyhow, that would remove the bit of logic associated with it and just have the raw data written down. But for the moment, let's just write these things out. So we want to, okay, I think we have the right data assets at hand now to write out 4 rules, sorry. Each of these rules here, basically. So let's write some code for each of them. And we're going to essentially concatenate the results together. So as changes to triangles flow through, where can we get those from? What did I do over here? I think, in principle, the arrangements have the changes in them as well, and we could just pop open any of those. I suppose we'll do that. So triangles AB dot, I think you have to do as collection. Which asks us to say for each key and value pair, a tuple to produce. And we're going to produce, essentially, we'd like to do A comma B comma C, but all that we're actually going to do is A comma B comma C, because our plan is to go in now and join with label. We're going to join with the noi label. I'm not really sure what to call this, actually. Let's call it rule 0, maybe. So we're going to repeatedly do some joins and build some things up here. And what does this look like when we use a propose of? So propose is the operator that adds new data on. So propose will take a label, and all that it really does is say, we're looking up. You got to tell me what the key is. So labels by edge alt, and then we need a function. So we're going to look up something about these triangles in labels by edge, and we need now a function that goes from these triples here. Yeah, we don't even need to do that, I don't think. Great. That's not. To whatever the key is. And in particular, we're going to do A comma B comma C goes to A comma B, because that's the key we want to use to look things up in labels by edge alt, because we're doing this first join, and we're producing delta of triangle join label. Yeah, and that's it. So this key selector function does a fair bit of work, actually. It tells us not only how do we look things up in there, but also how do we exchange these triples, so these triangle triples that are coming through. How do we shuffle them all around? And what we end up with, I'm pretty sure, is a pair. Comes out the end is a collection that is a pair of triangles and the label. So the type that went in paired with the value we looked up, which is a label. All right, we're going to do this again. Let rule equal propose, rule 0, equals propose of rule 0. Labels, again, this is just labels by edge alt. But now we have a slightly different setup here. We've got A comma B comma C comma label. And we want to produce A comma, we're doing C. Great. we now have a few labels here, and we could take a moment if we wanted to minimize those. So we could, for example, do let rule 0 get 0.map of I have no idea what this even looks like. Probably a comma b comma c comma l1 comma l2, except we need more parens. We could turn this into a comma b comma c comma std min l1 comma l2. That's nice of us to do, but we didn't really have to do that actually, because the reason we do it everywhere else in our computation, it's a smart thing to do generally. Like the reason we did it up here was because it was really important for us going into these joins to minimize the complexity of the record, because we were recording it. Like we were going to record all the changes. And if we had pairs of labels for which the min didn't change, well, if we don't want to record that, we'd love to just change it to be the min and see that it doesn't change, and then therefore be able to record a lot less. During this, the min doesn't really change too much. There's one fewer integer as we're streaming around. Let's get the last one out now. Propose rule 0 labels by alt, and we got to get an A, B, and C in a label, and we're going to use B and C. And we'll put a final instance of this rule down at the bottom, A, B, and C, L1, L2. So now we've got an A, B, and C, and a label. This is great. This is ready to be concatenated into our result. But we need to do some more rules, because this will only respond to changes in triangles. It won't respond to any changes in labels. And of course, the labels are absolutely the things that are changing iteration by iteration. So that's really important, actually. So let's see here. So we can just start writing down some more of these, and we can see where things go horribly, horribly wrong. Let rule 1 gets. So we're going to have labels by edge alt. So we want to use alt rather than noi, because I think we want to use alt rather than noi. Hold on. Actually, this is a good thing to check. What's the difference? All right, the difference is these are the changes to label by edge, but we've flavored each of them with an alt or noi flavor, where alt changes can't see noi changes. Noi changes can see both noi and alt changes. So I think we want to use alt changes so that we have the ability to hide things from it. Right? If we had used noi changes coming in, we would only ever be able to encounter either alt or noi changes, and we'd see both of them. See meaning these timestamps are less or equal to noi timestamps. So I think we want to use alt timestamps so that when we use alt timestamps, those are less or equal to ours. And when we use noi timestamps, those are not less or equal to ours. Pretty sure. Let's check and see if that was right. Changes over here, when we brought changes in, see, we just said enter, but enter uses the default, which is alt. So yes. As collection, and we need to say for an edge a comma b and a label, what do we produce? And I suppose that's going to be, I guess it actually isn't a comma b comma. Let's try to get a similar shape, I suppose, as the others. And now we're going to join this against triangles, right? So if we have A, B, and label, triangles is a really good thing to join against, because we immediately get a strong restriction on C. We could join with label of A comma C. That's going to give us a lot of crap. Like, it's going to give us all of the C's adjacent to A, not only those that are triangles with respect to A. So this is just a much better thing to join by next is triangles. So let rule 1 get propose rule 1, and now we want triangles AB, I believe. And we need to indicate how do we get something out of our A comma B comma L tuple for a key, and it's going to be A comma B. And now what we have is a weird pair rule1.map a comma b comma l, because that's what went in, comma c. Okay, kind of weird. So let's make that be a comma b comma c comma l, sort of like we have elsewhere. So we've done this much of our join, and now we want to go through and join against the other labels out there. Essentially, we're looking. We've experienced a change in the label for AB. We need to see if this actually manifests as a change for the label in A, B, and C. Might not. That might just end up suppressing things. But let rule one get propose rule one labels by edge noi. Okay, so what we're doing here is saying the first rule that we're going to have fire of all these labels is the AB update. And that means that we can absolutely, if there were concurrent updates, we can see any updates to AC and to BC that have happened previously, but any that are happening concurrently, for some reason we don't get to see them. And that's mostly so that when we derive them in subsequent rounds, we don't end up over-deriving anything. So we're going to use labels by edge noi and go from A, comma B, comma C, comma L to, we're doing AC to A, comma C. And now we have a weirdly structured A, comma B, comma C, comma L1, comma L2. We'll do our stud comp min L1, comma L2. Great. Friends there. A lot of semicolons. Apparently, I'm just forgetting to do this. And now we'll do the same thing again. Again, using labels by edge noi for BC. BC out. And we are now good to go. This is ready to be concatenated in as well. Now, okay, I'm going to copy paste this. We're going to fix things. And you're going to see the classes of things we need to fix. Possibly, you're not going to see some classes of things we're going to fix too, and they're going to be bugs. But like one thing we're going to need to fix apparently is this sort of crap all over the place. Maybe that wasn't so clever doing the copy paste. All right. Well, we still have our labels by edge alt coming in. We want them to be alt. Possibly in the very last one we could have used noi if we wanted, but we're just going to use alt for each of these. If we want to be grown-ups, we should probably go through and change these bindings. This doesn't change anything at all about the program, but it keeps our brain a bit more clear about what's going on. So I made an important change there. A bunch of not important changes where I changed the B's to the C's, but I did make an important change when I changed the B to a C here. We're now joining AC by triangles where we're using the first and the third attribute rather than the first and the second. And it's a different set of triangles that we find there because they're maintained in this ordered representation. Just different triangles are found in different places, indexed by different keys. So we did that. We got A, C, and B in the label. Let's put them back into ABCs. This will make our life a little bit easier for the rest of the computation because it's back in some canonical representation. Now, we have alt things coming in here, and when we join with, when we're going to look up our AB labels, we're allowed to see them now. So they've already happened logically. So they've already happened. We're now allowed to actually look at them. We're not going to use AC as the key. We're going to use AB as the key, which is important to remember. And then, just like above, actually, we'll do a join with the same labels and BC with noi because we don't get to see new BC labels yet, and everything is essentially just as it was before. let's make some similar changes down here. BC, BC, this is just to tidy things up. This is an important change where we change which indexing of triangles we use, but this is not important here where we change the variable name, other than your brain will never stay in the right order if you don't do these sorts of fixings. Like trying to debug what's going on here without the correct variable binding names is just a disaster. All right, now we have labels by edges alt coming in. We should see both of these, so we're going to make both of them into alts, giving us visibility into concurrent changes with both of these labels. We have BCs coming in. We can do this however we want. We're going to do ABC, AB, and then AC in that order. And now I think we do rule 0.concat, concat, rule 1, we just do it a few times, 2, 3, dot leave. Triangle labels, yeah, great. Now, triangle labels. Any bets on whether that actually compiles? Let's check. No. Okay. Oh yeah, of course. Well, I forgot to put a semicolon at the end of this crazy logic I did up here. That's probably why it didn't compile. No. Ah, right. Okay. Well, one important thing is that we need to update our cargo.toml to point at the dogs repo, which is forget. We can just. I'm going to just try some things. I haven't actually ever done things this. I was going to point at a local repo on my. If that works. Oh, spurious network error. Oh, awesome. All right. Let's I don't know if that's actually spurious or if that's Wow. That's not normal. Gee whiz. Okay. Let's let's change this a little bit to be some local stuff. So we're in some work in progress thing. So let's just make this be timely dataflow. Differential dataflow is also local. And docs is we get to wait a bit as creates, I guess, times out or something. Who even knows? Doo-be-doo-be-doo. So typically what this means, let's check. Typically what this is a class of error that if you've not seen before, you'll see a lot. Trait blah is not implemented for some other thing where you're pretty sure that it actually is implemented. And usually what this means is that we're pointed at incompatible versions of different things. So if we look at docs and say, what version of timely do you use? It uses the GitHub version. If we look at differential, what version? Hopefully it uses also the Git version. So we are going to stay with a Git version of timely. Okay, cool. Now we've got a lot of other fun errors. So range by key 103. What? 103. How did I? Oh, it wants me to put the use statement there. That's nice. 170. No, sorry, 171. Let me fix that. We're not using validate anymore. Validate is useful if instead of proposing values, you wanted to restrict, essentially wanted to do intersections. And validate's important because it does that much more efficiently than just proposing its own values. So if we have a relation that had 100 values that it might have proposed, we could go and propose 100 values, but you'd much prefer if someone only has 5 that he wants to check against that list, that you do this more efficiently than proposing 100 of them and checking their intersection. It turns out that this is important for things like triangle computation, worst case optimal join. We're not going to do it here. All right. It's a little stressed out about shape of triangles, which maybe makes some sense. 174. Well, 75 now maybe. Our triangles are not actually ABCs, they are, I fixed it up here so I don't have to do it too often, BCA triangles for some mental reason. Alright, and it's complaining about that a few times. No method scoped, so we need to bring in some scope methods. Great, some mismatched types, expected arrangement found of reference. So if we remove the borrow, so I think we probably just need to do some cloning here. So I guess it doesn't want to do the cloning for you for some reason. I don't know. But we can move in ownership for these folks. Arrangements clone very cheaply, so it's not actually all that interesting. Something is wrong here. Yeah, they should all be Noi, I think. We don't want triangles to see concurrent updates to labels, because then they'll be rederived. One conclusion you might have from all this is, couldn't you do this for me automatically, Frank? This is terrible. To which the answer is yes, absolutely. Get your checkbooks ready. That's absolutely something that we'll be doing. Hey, and it builds-ish now. I'm going to go through and tidy these things up just to make sure that cleaning up all of these unused variable things is a great sanity check to make sure you, for example, did the right replacements in various moments. So we should be able to trash a B and a C, and the rule should be here that when we're doing A, B, we're going to have one case where we ignore the B, one case where we ignore the A. When we're doing, is that right? Did I just make that up? Yeah, I'm just talking out my ass. Same thing is true down here, but didn't have to be true up there. When we're doing triangles, we ignore all 3 because one at a time. And when we're doing AC now, we should have one where we ignore the C and one where we should ignore the A. We're doing BC, we should have one where we ignore the C and one where we ignore the B, which we do. Let's see if this is, we got some more. Ooh, we ignore the, oh, to find the key, yeah. So in all of these, actually, when we're trying to figure out what the key is, we ignore the label. That makes total sense. That's also true for triangles, or when we're looking things up into triangles. Yeah, brilliant. All right, 201 and 203. 201, something good. 203. Great. Well, let's try it out. It's probably going to be massively wrong, but it's fun to run code, so let's get this building and run it. And in principle, we still have the old code here that we could copy and paste back in. This certainly was a much more concise way to write the same thing. And it's possible that actually, because we've blown things up, the complexity up so much, we might even lose actually by doing this. That'd be too bad. I mean, we should win asymptotically. We should win for much larger data sets because we are maintaining a lot less state than we were maintaining up here. And a lot of the work that goes into differential data flow, compute-wise, is maintaining collections, keeping accumulating changes and keeping them in an indexed representation that supports efficient random access. We're just not doing a lot of that anymore, which is great. And cross our fingers, and hopefully the computers will go faster because of it. All right, it's running. What's going on? Nothing happened? Awesome. We're for sure using a lot of memory still. Does that make sense? Ooh, and it's climbing. If I had to guess, I would say this is looking a little bit slow at the moment, though it's also one of the other slight changes with these operators that we've described is that they're not as well regulated as standard differential operators, who carefully pause and don't start doing work until they've made sure that things have been minimized down to some appropriate representation. These operators, because they're not stateful, just sort of barge ahead and do all their work, and that can be a bit gross. They can spike the memory use up quite a bit. So went back down, so that's reassuring. But it's definitely slower than before. I wonder if we're going to be able to. One thing we should probably do is make two programs so that we're not commenting in and out things. And then we can spin up a timely profiler or something like that and see which of these folks takes all the time, where do we do all of our work, that sort of thing. We are now, for example, though I don't think this is the killer, we're maintaining triangles indexed 3 different ways, whereas previously, I guess previously we had it indexed a few different ways with labels attached to it. But let's see how this pans out. So it was 200 something versus what I think was, what did we agree, like 105 seconds single threaded before. Um, yeah, this is looking pretty poop. I wonder what. This is interesting for me now. It's maybe not so interesting for you watching along, but super interesting for me because I am generally really excited when there's something to fix. Like usually something to fix means there's some way to improve, which is awesome. And figuring out, for example, who among all of these, the memory footprint still, is the memory footprint, for example, I would say is sort of friendlier than I think we saw it before, which I felt like it was up in the eights of gigabytes. So that's nice. Perhaps a conclusion then is that we are, if we're computing the same thing, like we could be screwing that up. But if we're spending a bit too much time just sort of flopping through all of these operators, that's silly. Whereas previously we just had these three operators in a row, each of which did a lot more work. Yet, like any change that came in here to labels, and it just does a lookup and sees what's going on. Whereas now we're sort of filtering through, saying go back and ask triangles again. Come back out here and join with a few more labels. And, all right. So let's see. So it's I was wrong, right? Do we agree? 91 isn't something we should be seeing in the output. 34 is where we're supposed to end up. So we could just have a wrong computation. Like that's nice because often when we fix, so this seemed very similar, I think, to what we saw before. But for some reason now we're seeing 91. Crazy. I mean, things could go up a little bit, but we don't think we're supposed to actually reach that. So my guess is that there's some sort of bug in all of this. I wonder what a good way to figure out what the bug is will be. I mean, in principle, what we do is we write both of these rules side by side. And we do a diff on them. And then we try to figure out when do they first go wrong. And then we try to track down the crummy tuples that made them go wrong and realize, like, oh yeah, that was a mistake. But just gonna read through these myself just to make sure I get them. Actually, let me. So we pop over here. We got some forwards, some reverses. We don't care about forwards and reverses. We got some alts and some noise. And for early rules, we use noise, then a mix of alts and noise, and alts, and eventually everything is alt here, everything is noise here, alt and noise in the meantime. Yeah, it looks great to me. Noise. Where did we come up with enough crud to get us up to 91? Barf. Well, let's triangle labels, old, negate, concat, triangle labels, consolidate, let's say, so what we're doing is we're taking these two collections, we're negating one of them, merging it with the other ones, and saying, cancel out as much as you can. And I'm going to start just by saying, we should map each of these to the empty tuple and inspect them. And this isn't going to show us the data indifference, but I suppose, actually, let's do that. Let's actually look at the data indifference. I was a little worried that if it was enormous, we would be overwhelmed. Right. Oh, if I screwed up. My parens wrong here? Yeah. New method join map for a collection of that stuff. Okay, we changed how triangles are shaped. That's right. So let's just put it back, I suppose. All right. Now, so we got a bug. We have at least one bug. The labels we bring in, both with alt and with noi. Triangles we bring in all at alt. And we have arranged those AB, AC, BC. Looks good to me. Triangles is ABC. Great. I was just going to take a while to compile, so we can just chat while we're doing this. Our triangle rule comes in. We join it with noi labels using first AB, then AC, then BC. It should be exactly the same thing. We're joining against labels by edge. And we keep them in. So by alt, AB, so we got all just roll ones, roll ones, roll ones, roll twos, roll twos, roll twos, roll threes, roll threes. Okay. Triangles AB using A and B. Swap that label to where we want it to be. We got our AC and B, here we got BC and A. Just making sure, like, a common blunder is if you copy and paste something that looks like this. You take this thing, you always put it in the third position, but that's wrong when it was semantically B or semantically A. Yeah, nothing leads to mind. So the result seems sort of right for the first round of changes. It's, so we might not actually see any glitches until it'll take a while. We might not see any glitches until the second wave, basically, because that was when we first started seeing buggy answers. And it could totally be that the alt noise stuff is glitchy. It hasn't been especially well exercised, I would say, for example, inside of loops. Printing out all this crap, and also just printing out answers but not actually calling them sorry, printing out errors but not calling them errors. So what I'm thinking about, sorry, I'm quiet because I'm pondering. The alt-note timestamp wrapper is meant to wrap an arbitrarily partially ordered timestamp with the property that um, when you compare, let's say, alt to alt, noi to noi, you get the timestamp comparison. When you apply alt to noi, you get the timestamp comparison. And it's only when you try to compare noi to alt do you get a bit of a glitch. And it's meant to be basically the same as saying your old timestamp paired up with 0 or 1 with a lexicographic order on them now. So when the two timestamps have an ordering between the two of them, we use that. When they're tied, we use the ordering on the second two coordinates, which is the lexicographic combiner. And it for sure makes a lot of sense when the first timestamps are also themselves totally ordered. We're now in a world where they're not totally ordered, and it's supposed to work in that case. Or at least, I hit my head against the wall trying to make sure it worked in that case. But it's possible it doesn't. And we would first notice it only once we saw the first not total orderedness of timestamps, which is the changes in the second wave of data coming past. We're just going to crack open the definition of those delightful alt-noi things. So alt-noi really is, it's a time and a bool, and it's really meant to be compared essentially as if the two times are equal, compare the noi field, otherwise they are equal. Sorry, if they're equal, compare the things, otherwise you use exactly the comparison between them. So two unordered things remain unordered. Alt-noi doesn't make them, allow them to see each other if they were not otherwise visible before. It's really only for introducing a bit of a stagger at equal times. And probably the complicatedest bits of math, most likely places for bugs, are the join and meet operators that take two alt and or noi times and tries to find a least upper bound and a greatest lower bound for the two. So join is the least upper bound, for example. And this is what I thought was the logic for finding their least upper bound. So, for example, at the very least, you have to take the least upper bound of their times. I'm not sure I can talk through why this is correct. I don't even know that it's wrong. So I'm staring at it myself. I'm not even clear that it is necessarily wrong. There could be other glitches that we've had in building up the query. What I'd love to find, actually, I wonder if this is possible. There's a version of the data that's just a lot smaller so that we could minimize the error and actually get it to manifest a bit more quickly and with a small enough amount of data that we can inspect it. Holy cow, 11:46. It's I haven't had breakfast yet, and I've been awake since 7. I may be having a low blood sugar moment here where we have to pause the recording and come back to it in a little bit. In fact, let me do that because my brain power for debugging advanced lattice stuff is blocked at the moment. love to get some food, lie down for a little bit, and maybe attempt to try to repo this on a smaller data set. So we'll stop for the moment and look for more of this in the future.